Hello all and welcome to my second video about the analysis of neutron detector array data from the NAND array at IUAC New Delhi. In this video I am going to take you into a journey about how we can prepare the neutron spectra gated by fission. In the previous video, I had already explained the concepts required for slicing the multi-wire proportional counter into different sections, and in today's lesson we are actually going to work towards that. Alright, so if you have any doubts or questions, as always, be happy to contact me on my Gmail and I will be happy to answer you. Now here we are going to work about the first thing which I want to explain is that working with the students for some time, I have noticed that the quality of the programs written by the students using root is not at the level which it is required for doing this kind of work. We have to write a structured program. All the programs which we write have to be structured. Now, what is this structured programming? This is what you are going to learn now, and it's important that you first make yourself familiar with all the root commands and all the features of root. The ones which we require for our work are given in my root channel. This is the address of my root channel. So if you haven't seen these videos already, have a look or revise them. If you have seen them recently, then it's okay. You can get on with this current lesson, and whatever is required will be explained here in this video itself. I am going to work with a sample file. See, in order to explain what I'm doing here, we actually need some data. Now the data files are very big, and so I can't really place the data files and make it available for you on my website. So I have taken only a small sample file. The name of the file which I am going to use is called IUAC NAND data.001. It's actually a root file. In this Rose-Niaz system, you will get, when you do the experiment, several files with this file extension name 001, 002 and so on. These are your data files. They are actually root files. So strictly speaking, they should have been named with a .root extension, but they have not, but doesn't matter. It's still possible to open and analyze them in root. So generally the names of the files which you will have would be corresponding to some projectile target system and the beam energy. And we will take all the files together which belong to the same target projectile system and that same beam energy to analyze together, and we would be placing these into a T-chain. A T-chain is a group of root files which are placed together in a chain so that in one go we can analyze the entire data. So here for my demonstration, in my chain there will be only one file, but for you there will be all the files which belong to that target projectile system and beam energy. And the program source code files which I am going to demonstrate here, they will be packed and made available to you through nand02.tgz, again a tar zipped file which you can unpack and you can get your program file. So all the source codes which I am using for demonstration are available here. So these files are actually good enough for all your data analysis work. It will be self-contained. You won't have to write any more codes on your own except making minor changes in the codes which I am providing you. And these files, both this sample root file as well as the programs, they can be downloaded from my website. So you can, if you don't yet have data, or even if you already have data, your first step would be to analyze this sample data file by following the video strictly as I am doing here, and get used to the idea how you are going to do the analysis. Now my website is ambarchatterjee.com, and you can connect there. And on the opening page you will find a link which takes you to the page for the neutron array, and in that page you will find available the links for my today's lesson 2, which includes this sample file IUAC NAND data 0.001, which is a root data file, and you will find a tar zip nand02.tgz from where you can extract the required program source codes. Now, okay, so what I'm going to do here is go very slowly and step by step. First, we will write one small program which I'm going to call program 01, prog001.cpp. As usual, I am going to work with files like like prog001.cpp, which are actually dual use macro as well as complete programs. So I am going to use it as a complete program, but you can also use it as a macro. For program 2, we will see that we are going to use it also as a macro. So this concept of writing root code, which can be used both as a program, complete program, as well as a macro, depending upon the situation. This is something which I have explained in my root series of videos. You need to revise that if not already. All the programs which I am going to present here will be dual use type, and we shall use it depending on the situation. We could be using it as a macro, or we could be using it as a complete program. So the first task for us is to discover the name of the tree and the name of the leaves. This I have also explained in my series of lectures on root, and all of you know how to do this by using the T browser. The other way to do it is also from the ls command. From the command line you can get it. Actually the tree name is going to be Rose Nias. ROSE is spelled with a capital R, the rest of the alphabets are small, and then Nias is in capital letters, NIAS. This will be the name of the tree inside all the data files which you're going to get from NAND. Now, when you look at the file itself and you examine the file with the T browser, you'll notice there are actually two trees inside it. And that's because when we are doing data acquisition, it's usually useful to have a safe copy. That means you have one tree which is having a data, and for safety you have the second one. As far as we are concerned, we do not need to mention, so it will be Rose Nias semicolon 3 and Rose Nias semicolon 4, for example. And the last one, that's the one which we shall use for our analysis. Whichever is the last tree, that means if it is semicolon 3 and semicolon 4, then it's semicolon 4 that we will be using for the analysis, but we don't have to mention that explicitly. So when we give the name of the tree, we will give only Rose Nias as the name of the tree. We will not mention the version number, and it shall always pick up the latest version. That is how you will do the analysis. Never try to give the explicit version number. And of course, in our demo file, they won't be this situation. We will have the tree. We won't have 3 and 4. I think we have probably got 1 and 2 as a demo. But anyhow, just use the tree name as Rose Nias, and that will work for you for your actual data, and it will work also for us in this demo. So to demonstrate this, I'm going to start with a very simple program. It's called program 001, and what it does, this program 001, is that it actually finds out the parameter list. See, the thing is, you all know how to get the parameter list in other ways, like from the tree browser or from the .ls command. But we are going to require this list of leaves quite a lot, because there are going to be, now you know, there are 111 neutron detectors, and there are other parameters associated with the MWPCs. So the total number of parameters is going to be quite large, say around 160 or so. Maybe more in some of the experiments, or maybe less if you are not using all the neutron detectors. But this list is very large, and you are going to refer to this list quite a lot. So you will not be able to remember the names of all the parameters all the time. So we are going to try to create a text file. The name of the file will be called paralist.txt. It will have two columns. The first column will be just 1, 2, 3, 4, 5, 6 in sequence, giving the number and the parameter a number. That's just for our own ready reference. What is important is that in the second column, there will be the names of the leaves. So to do that, to create this file, we are not going to do it manually. You can create this file manually if you want, after having discovered the names of all the leaves from T browser or from the .ls command. You can try to type out this paralist.txt, but that will take you a long time and it will be error prone. So we are going to do it programmatically, and the way to do that is a command which I haven't introduced earlier in my root videos, and that is you take the tree, tr is the tree, for example, if tr is my tree, and then with the arrow operator you give the command to get the list of leaves. So this program is going to use this get list of leaves command, and then there is also further accession required by putting the at this property, this and then putting an index I which runs from starting from 0 and goes up to the total number of leaves. And then one more level of accession is get name. So this procedure gives you the names of all the parameters, and then we are going to save it to paralist .txt. So this is actually our first step to adding structure to our codes. Later on, our code will access this list of leaves by number rather than by name. I mean, we'll have both the options. We can of course still refer to the parameter by its name as we usually do, but this is our very first step which is required in order to work further and make our programs structured. We shall see how this can be done. So I'm going to now go on to running this program 001 and explaining it for you. So as usual, make a directory, download the TGZ in that, and then unpack it. And then, so right now I have already unpacked for you program 001 and also program 002, both the programs we are going to look at first, and then we will unpack others also as we go ahead. So let's start with program 001. So basically this program 001 looks like this. So it's short, I have shown 33 lines, of which the lines 25 to 40 to 33 are simply the lines which you have to write in order to make a dual use program and macro. So this program 001 could be run as a macro, or it could be run as a complete program. Right now we are going to run it as a complete program. That will be good enough. So how do you do that? First you have to compile it. If it's a macro, then you don't need to compile it. If you're going to run it as a complete program, then first you need to compile it, and the compilation command I'm highlighting for you, you can see it here. So this will compile it. These are at the top of it, the includes. If it's a macro, you don't need these includes, but having them is no harm. But if it's a complete program, then you know that these includes are absolutely necessary. I've written this program so that it's structured, and it has got capability of handling up to 500 parameters. The width is in the name. That means how many characters can you have in the name. This I have kept 40. So this is just a way of doing it for you. You can get an idea of what we mean by structured programming if you look into this program, which is the program itself, which is only from 15 to 22. It's a very short program. It has only one purpose, and that is to write the list of leaves. So first we in our program we define this program, this file. Now to get the list of leaves, I'm going to get the list of leaves only from one file. We don't need to here make a chain, and we don't need to look at all the files, because all the files for this beam energy and for this system they would have the same leaves. I assume that the name of the tree is Rosnias, because that is the convention being used at IUSC for all the Rosnias, all the data. So when you have taken the data at NAND, the name of the tree is going to be this. For this program, I assume a fixed name. I am not trying to discover the name here, although that can also be done, as you know. All right, so there's going to be the file which we are going to create will be called paralist.txt. So we got to make an output stream, and we got to give it a name paralist.txt, so that when we get the leaves, we'll be able to write the list of leaves here. So this is the loop. This goes over uh, the list of leaves. So the list of leaves is available in this tree. So tr is my tree, and when I do tr and make a pointer to get list of leaves, I will get the leaf list. And if I want to know how many leaves are there, what is the total, so this is a list, and with all lists in root, you can get all the entries, that is the number. You can get the number by this command, get entries fast. So get entries fast will tell me how many. So I need to run this loop over that. And just for the sake of this file, when I actually this list will run starting with an index of 0. You know that in C programming, all indexes, they start with 0 and onwards. But when we talk in common everyday language, we ask what is your first leaf. So we want to number the leaves from 1 onwards rather than 0. So this is something which I have done. I have just added 1. So in my output file, I am going to write I plus 1 rather than I. But you know, it's not very important. Later on, when we are using this file, we won't really be making use of the first column. We will be making use of the second column onwards. And in our loop, again, we can run from 0. There's no harm. But this is just, you know, so that we get numbering starting from 1, and we can look at this list. So this is it, and just as you have get entries fast, similarly you can make a pointer to get name. This get name command, this gives you the name of the leaf, and so that's it, and then we just close it. So what will happen is that when you run this program, you will get a file, and the name of the file will be called paralist.txt. So if I look at my directory as it stands now, since I have already run, I have this paralist.txt, so I'm going to delete it. So now it's gone, paralist has been deleted, and we will try to get it created by running the program 001. So this is my program 001. I have here just at this moment loaded only program 001 and program 002. Later on we will get the other programs also which we need. This is my sample file, IUSC 9 data 001, from which we are going to get the names of the leaves. So as usual, you go to this folder. You go to this browser of this folder, and then you right click, and then you say open in terminal. So now my terminal is open, and it's opened in this folder. I can make it bigger for you by pressing Control. So after we have pasted this compile command, we compile it like this, and now the program is ready, program 001. We can run it now. So I'm running it. The name of the program is prog001, and I'm executing it. And now it says that this paralist has been, now since this was a dual use macro program, so it is at this point you will always have to put Control C when you want to quit. Otherwise we are inside this loop, the app.run, and to come out we press Control C. That terminates. And now if we look at our directory, then so this was the executable, it got created, and now this file is new, paralist.txt. So this file now contains 1, 2, 3, 4, etc. in column 1, and the names of the parameters such as multiwire proportional counter, 1 timing, the first one, the second one is MWPC2 underscore T, and so on. And this goes on the full list, and as you can see here, I have got 156 parameters in this list. So I'm going to work with these parameters and have successfully saved it as a text file. Now, this was, as I mentioned, our very first step towards going for structured programming. So this first step is necessary for utilization in the next program, and gradually we'll learn what do we mean by structuring. So now I go to the next step which we have to go towards, and that will be the second program. So in the second program, prog 002.cpp, and this program, by the way, we will prefer to run it as a macro. I'll show you why. And the idea of it is to do or create the gate which will define fission. It will be actually a T-cut which will help us to define the fission. So program 2.cpp will, again, it will be a short structured code. The aim of the code will be to create the gate. Now, if you know, you already probably know that this gating is done by making a T-cut in the plot of TOF1 versus this is called in MWPC T MWPC1 timing versus MWPC2 timing. So here you see that figure, not this inset, but this is the figure in this published paper. Okay, so if you refer to the paper, you will see this figure. We are going to try and make it ourselves now. So when you run this program 2, I'll explain program 2. In program 2, I have plotted the singles, the one-dimensional spectrum of MWPC1 versus MWPC2. And I have also plotted the two-dimensional plot of MWPC 1 along timing along the x-axis and MWPC2 timing along the y-axis, and that gives rise to the same plot which you have seen here, which is also demonstrated here in the published paper. The idea of this here is that later on we are going to select the fission event. The fission events are here, and this second patch, this is elastic scattering. So if you look at these figures, then this first big wide peak, that corresponds to fission, and similarly for the second MWPC also the fission is in this one, and the beam-like particles which come from elastic scattering and direct reactions, that gives rise to the second peak which we are going to avoid. And when this kind of reaction happens, elastic scattering, then there is elastic recoil, and that I call target-like, that goes into the MWPC2, and that creates the second this left side, which I have called here target-like. It creates counts in this region, and there's also elastic scattering going into the second detector, second MWPC, that is giving another peak here, but that doesn't have a partner which goes into the first detector. So anyway, we won't really be putting any gates on these two singles one-dimensional files. The gating will be done by drawing a T-cut over this part which I have shown here as the fission, and in that process we will be eliminating the elastic scattering. In the figure which you see here, they have drawn the gate here very tightly around this. They have avoided the periphery, but we are not going to do that. I feel it's not required to be so strict in this. So I would prefer to make a little bit wider. I would still avoid the stray events which are seen here sometimes going out. So I would put a gate, whatever I feel more comfortable with. I will show you that. And how do you then save the gate, and then how do you use it later on? This is what I am going to explain now. So let's go over to program 2. So program 2 code is like this. So this is my program 2 code, and as usual I have created the .h files. I have included them here at the top. Whatever you need I have put here. These are very important because when you try to compile, you will get compilation errors. For example, here now I need this tchain .h because I am going to make a chain. So I need it, and I am going to make use of the tree, the leaves. I am going to make histograms, so I need th1, th2. So be careful on these headers. Okay, so program 2 starts actually here. So this part, from line 74 to 82, this is the formal part of it in order to make it a dual use program and macro. We'll be running this one as a macro for our real work, but we'll see why. And the program itself is given here. This program has got, first of all, we try to read that file. The first job is that, well, okay, here first I think we have created, yes, it's here. And then we'll make the change. So this get paralist, okay, is a short function call. It's here. This get paralist is a function call, and in this way I can recover from my file paralist.txt which I have created in my first program. I got this file ready. Now I'm going to read it so that I don't need to get the list of parameters again in the procedure which I have demonstrated in program 1, but I can read it from the file. Now you understand what we mean by structured programming is that we create functions, small functions like this. We don't clutter the main program. The main program should be short. This is one of the things about structured programming is that your real work program should be short, and it should call functions, small functions which do the work. So the first function which I am calling is to get the number of parameters. N par is how many parameters there are, and in that process it will fill up this array p name. So p name is the array which is going to hold the names of the parameters. So paralist.text, I read it and I get how many there are and I get that names. This is what I do first. And this second part, n files, this is for getting the files which I'm going to. As I told you, I have only one demo file, so I'm going to have only one. But for you, for the same target projectile system and that same beam energy, you will have several files. You need to get all those files and make a chain out of it. So what I have done is I have created, now this is done by hand, so this is not something which is generated. You have to type this file yourself. I typed it here. As usual, in the first column I put 1 2 3 4 to number the files, and then I put the name of the file. I have only one demo file, so I have created it here. If you had another file, you would go to the next line, you would write 2 here, and then you would type the file name over here. That's how you would do it. So anyway, so I explained to you this file list.c. So I read that, and that tells me how many files I have on the base and the names. This names is again in a character array, that is NF name. So with the help of that, I can create my chain. So this is my chain of files, and here I have created my chain. And how many entries do I have in the chain? Not in the file itself, but in the chain. That is obtainable by through this command get entries. So get entries tells you how many events I have, not in only one file, but in all the files combined. So this I am printing it out here so that we know. And one tip to you is that later on, now here in this program, for example, I'm going to have a loop over entries. So when I loop over entries and I build a spectra, this process for me today it will be very fast because my file is small. But when you do your analysis, there will be many files in the chain and each file will be big. And when you do the analysis, this process can be slow. So what you do is that you change this program and don't loop over all the initially. Finally, you have to do this way only. You have to go over all the entries. But here you put a smaller number, like say 50,000 or something like that. You put a small number here manually while you are checking everything is okay or not. Once it's running smoothly, then you let go and let it run for the whole thing. That's for your final analysis. But initially, when you are just trying to check, that time you can restrict yourself to a smaller number. Okay, so next I define. So I am here in this program, I am going to build 3 spectra. The first spectrum is going to be my MWPC1 timing, MWPC1T and MWPC2T. These two, the timing in the two detectors. This gives you the time it took for the particles that this MWPC, it took how much time it took to reach from the target to this detector. So this is what is we are going to put a gate on this spectrum. So we don't need this first two, these singles, but just for our idea or knowledge, we are keeping this here also. But we are going to work on this one, which is a two-dimensional histogram of T1 versus T2, MWPC T1 versus T2. These are the first two parameters in our list. We are going to build that, and so you know how to do that. First of all, you got to make the branch address. Now you can see what I mean by structured programming. This one line here actually makes my set branch address for my entire set of parameters. So how many parameters did I have? I had with me 156 parameters. Okay, and I have seen students who write this set branch address for all the 156 parameters one by one, creating 156 lines at this page itself. So this is what I am trying to avoid, and now you understand why I created paralist.txt file, why I read that back here, and now my entire set of 156 set branch addresses has become just one line. Later on you will see how I will use that kind of technique for histograms also. I won't have to define the histogram line by line like I am doing here. There will be a loop. But for this first round, this is the only part which is really structured, and you can see how good it is, because you see a program which is basically short is easy to read, easy to understand, easy to debug. So that's why we make program structured, and it is less error prone. So that's why we make our program structured. So please follow carefully. We are going to introduce more structuring later, but right now this is the only element of structure which I have introduced to you. It makes use of the fact that our parameters are now numbered as P0, P1, P2. This is that branch address to which I will, and the names you see, I have stored the names also in a dimensions character string. So the names are here, and then I have defined my P, this quantity double P, this is going to hold the parameters values as we run through the loop. So now we can just start going over the entries in the data, in the chain. So I got my chain, I got my branch address setting, all in such a short number of lines. And I'm going to build three, and then I'm going to display the three. I have made three canvases and display. So this is how it will be. Let's run it, and then you will see the three canvases showing this data. We are going to, just for demonstration, I will run it as a complete program for you, but really what we need is to run it as a macro. We'll see why. What is the difference between macro? What is why we sometimes want to run as a macro, sometimes we want to run as a program. What exactly are we doing? This I am going to explain. So I will go to my command line, and I am going to first compile it. The compilation command is always in all my programs. You will always find that the compilation, I don't have to hunt for the command. It will always be as a comment in the first line of any program. So I can get it from here, and I can cut paste it here, and then I can, so my compilation is done, and now I run it. And when I run it, so now prog002, this is my prog002 executable which got created here after I did the compilation. Now I'm running it, and when I run it, you see in my file I have only 500,000 events. Okay, I have only one file as a demo, and in that there are exactly this many events. So this is a demonstration only. And okay, so these are the spectra which got created. Let's look at them now. So here is my first, second, and my two-dimensional. So this one, this is MWPC T1. I will just zoom out this so that you can see it, and similarly here I zoom out, and so these are, so this is corresponding to fission, this broad peak, and here this one. This corresponds to the recoil target like projectiles. This is again elastic scattering. with only one, the other partner not being detected, and this is your uh, T1 versus T2, on which this is the one which this part is going to be the fission, and so we are going to work on that part. Now, what is our next task? So, this is program 2 is running fine. We're going to run it now. What I want to do is I want to draw a T-cut around it. This is where the situation comes when I'm going to draw the T-cut, and then I have to save the T-cut. Now, it's possible that you could have done the T-cutting over here itself also. But that is what I don't want to do. So if you save it by drawing now a T-cut at this stage from here, you won't get a chance to save that T-cut in the way that I want to save it. You can still save it in an ASCII file as a macro, but that's not what I want to do. I want to save the T-cut inside another root file. So that you can't do now. So this is a program which is running and my terminal here is stuck. With this, I can't type further commands here. They won't be of any use. So I can't, if I draw the T-cut here, I can only save it through the GUI. So it's possible to use GUI and then save it, but that way I can't really do the saving the way that I want. So for this reason, I'm going to terminate it here, but I'm going to run it as a macro. So how do you run it as a macro? This I write it for you in my PowerPoint. So you can just use this command. You can say root and then give the name of the CPP file, or you can type just root to start root, and then you can execute it as a macro to load the macro and execute it. Either way. So let's proceed. So it says you can do it like this. Say root. So root is running. Now I say dot execute. Name of the macro is prog002.cpp. So this is a dual use file. It can be run as a macro. I'm running it now as a macro. And so you see, you've already run it. You know what it looks like. I'm interested in this one. So let me just minimize these for now. And here I'm going to, this can be also minimized for the time being. And what I have to do is, first of all, I have to draw the cut G. So let me first zoom. So I zoomed it. Now I am interested in drawing the fission gate. So I look at view and toolbar, and then select the scissors tool, which is the last one. It's called graphical cut or T-cut, and that is the scissors tool. I click it here. Now my pointer has changed into a cursor type pointer, and this you know how to do. I'm going to start here. I'm going to draw it carefully. I'm avoiding some peripherally points which are a little outside, far away, but not as tight a gate as you saw in that published paper. But I think what I'm doing is reasonably correct without losing statistics. I'm trying to draw a gate which I feel is reasonable. So this, and as you know, at the end you have to click twice without moving the mouse. So that's how you close. Now it's done. Now what I don't want you to do is that if you now want to do a right click, and then the context is the cut G, and at this stage there is a possibility to do save as. This I don't want you to do because it creates a macro file, and if you do that way, then to use that macro file again in the next program, that becomes more difficult, although not impossible, but more difficult. So the correct way of doing it is what I am showing you now. So I have drawn the cut G. Right now what I need to do is I need to go to my command line and proceed from there. So my command line is my terminal, which is here, and now the first thing is that at present whatever I have drawn, that is having a name cut G. See, if I say cut G, then you see that it's there. This is showing the address. So my cut G is the name, but I don't want this name. So first thing I do is I change its name. So I take cut G, and then I go to its property and I set name. I change the name. Let's change the name to something which will be more meaningful, and I am going to call it as cut T1 underscore T2. So this is my name change. Having executed this, Now the next two commands are not very necessary, but I think it will be nice to do it. So I'm going to change the names of the x and y variables also to be the correct names which we need. So now that the name of the cut g has changed, I put the new name here. The new name is cut t1 underscore t2, and then I put the arrow operator, and then I say set variable x. So set var x, and I give it the name. The name along the x-axis is actually mwpc1 underscore t. So I give it this name. This will be helpful for me, but it's not necessary to actually name these x and y. It would work even without that. So I got it. Then I will set the y also. So to set the y, I put here y, and I put mwpc2. So this completes my work in setting the names and the names of the x and y axis. Now we have to write it to a file. I am not going to write it into a macro C file, which is what it does if you do from here. So if suppose from here, if you were to take this one and then do save as, that would result in unnamed macro, and the tcut would be saved in that, but that I don't want to do. What I want to do is to save this tcut into a new root file. So we are going to create a new root file. The command is given here in my PowerPoint presentation. You say you create, so I want to create first a new work file, and this is going to be a root file. And in this I will not only save this cut, but I will have to save all the cuts which I am going to make later on in my other spectra, for example, then the cuts which I will make for neutron spectra when I work on it. So all my work I will save in this. I'm going to call it as work.root because I have only one chain and one file, but when you have working with many other data, then you give it a name. So because you'll be having different beam projectile systems at different energies, so you may choose a different work file for each case. So I'm going to call it work.root. So I'm going to create it by this command tf is equal to new. Then I will say t file, and then I'm going to call it work.root. So work.root doesn't exist yet. I'm going to create it now. So since it's going to be a new file, I have got many options here. I can say create, this is also okay, but I'm going to say recreate, so that in case it is already there, it will be overwritten. So I recreate it here, and this will create my new T file. And then I want to place my cut. So I have got a cut now, and that is called as cut T1 underscore T2, and I'm going to write it. So write, and I'm going to write it, and where will it write it? It will write in that root file which is current, and my current root file is the one which I have just opened. So it's going to go into this root file, and having done that, then I should close my TF. So TF should now be closed. We will use this for all our cuts. We will use the same work file and place other cuts in it, as well as any other histograms which we save. Everything will be done into the work file. I have created it now, and so that's done. Now I can complete it, so I can quit root. We need to record the positions of the gamma peaks in all the neutron detectors, because we are going to use that position as a time reference when we calculate the neutron time of flight, and this we have to do for all the neutron detectors in the array. So I have done that for you in a program. It's called prog003.cpp. So basically the gamma peak is, this one is the most prominent peak in the spectrum. You have to find out this position. Instead of doing it manually, so if you were doing it manually, you would have to actually display all these spectra, and then you would have to find out, locate this position and write it down manually. So instead of doing it manually, we have done the whole job and we are going to save it in a file automatically. So how is that done? It's done through this program which is called gpause, which is called program 3. And so program 3 is actually the effective part of it is here. So the only new thing is that I have made here end date equal to 73. You can change it to a small or bigger number depending on how many detectors you have. And then instead of having the spectra one by one, we have an array. So this is the way that you can do structured programming, and you can declare all in one line. You can declare the initializer for all the these th1s in one command. And for doing that, when inserting the name, I'm using a handy command here. It's called form. So if I use form, and then I have used here I plus 1 because I prefer to start the numbering from 1 2 3 4 instead of 0 1 2 3. So my H spectras, the names will be H001, H002, and so on. And then after having done that, this one you already know how to make up a chain branch address in a structured manner, so that you don't have to write all the chain addresses one by one, but in one go you can write all. So then now we make a loop over the end. This is my event loop over the entries. And you, for your case, you when you have see, I have a very small amount of data, so I can afford to run. I have only one file, and so it can run, and even then I will have very poor statistics. But for you, you don't need to run over all the entries. You can run through a smaller number, say 10% of the entries, depending upon the situation you have, to save time. But anyway, for me, when I run it, this will run very fast. So you can see this is only to locate the positions of the gamma peaks. We don't have to put all the statistics into it. So this fills this H array. The only extra thing I need to tell you is the indexing. So I have used parameter 2j plus 11. That comes from here because the first 11 thing is to be skipped, and this one is my very first time of flight. It's at 12, which means actually index wise it means 11, numbering wise it is 12. So when my j is 0, I will get P11, and that is my first time of flight. After that it will go in steps of 2, so that's why I have put 2j. So this is how I will get all the TOF spectra. And having got that, then when the program reaches this point, then I am finished with generating all the spectra, and all I have to do now is to write the data which I have got, not the data yet, but locate the peaks in it and then write that peak position. The way to get the peak position is done this way. First you take the spectrum. I am doing it in a loop. You take the one-dimensional spectrum and select the x-axis and then set range user. This is what we have to do to decide upon a region of interest. So I have chosen very broad because this gamma peak is the only one which is there. The only other peak which is there in the data is the very first channel, which we want to avoid. So setting it over the whole range, almost the whole range, is good enough. And then I have to proceed with get maximum bin. This get maximum bin, this works in this region which you have set using the set range user. So that's why this has been done. And then after having got the bin number corresponding to the maximum counts, then I ask for its position, and the position is obtained by doing get bin center. That's about it. And then I have to print it out. So I have opened my file. I call the file as gpause.txt, and then I save it with this, and that's it. Now if you just compile and run this program, so compilation command is given here as usual, and then you run it, and then it will result in a file, and that file will be get created, and it's called gpause.txt. So gpause.txt, after you have run this program, will get created, and in this file you will have for all the 73. You see, this is my first detector. It says that the peak position is at 3226, and like that it goes on, and in the last one, my 73rd detector is located at 3286. So this is the file which gives the gamma. You get it in an instant. So that's the way which we can proceed. In order to select neutrons in the neutron scintillation detectors, we need to make a t-cut in the two-dimensional plot of time of flight on the y-axis and the PSD signal along the x-axis, and this has to be done for all the 73 detectors which I have. Now you can see an example of it in the published paper. This is what it looks like, and now we are going to actually do the same. The first step will be to build all the 73 two-dimensional spectra with PSD signal along the x-axis and time of flight along the y-axis. So for that, again, we have a program which is structured and short, and it is similar to the previous program. So this program looks like this. This program looks like this. The only effective part of it is which you need to understand is that the number of detectors, I have put 73. You can change it as required, and then after that I have an array of H spectra, and the constructor for these H is done in one line in a loop. This makes the program extremely short. What you see on the screen is the only effective part of the program, and after the event loop runs, then it actually updates the spectra. The pattern of the parameters is this: 2j 2j plus 10 along the x-axis and 2j plus 11 on the y-axis, according to the parameter list which I have. Hopefully it is the same for you, but it could be different, so you can adjust it accordingly. And then after the spectra are created, then it's going to open. Now work.root should be open in update mode because it already contains the T1, T2, T-cut, which is for fission selection. And to that now I am adding all these spectra. So that's how this will work out. And then we have to proceed to the next step. So let's first finish this part. So I open it in the terminal, and in this one we are going to first compile it. So the compilation command is for this program over here. This will compile it. So I have it here, and that's the compilation. Then I execute it. So when this executes at this stage, the see, it says done. Now you put Control C and come out. So at this stage, my work file, work.root, this contains, in addition to the earlier t-cut which I had saved for fission, it now contains all the 73 two-dimensional spectra. Now that we have completed that part, the next step would be to draw the t-cuts for all these spectra and then save it again in work.root. So this we are going to do from a command line root session. That will be the simplest. So how do we do it? First we start root. We started root, and then we know that we must open the file in which we are having the spectra, and that is, this is the command. It should be in update mode because we are going to write the t-cuts into it, and we don't want to remove anything, information which it already holds. So this is my command by which I will keep my t file open, and then I must get that is retrieve from it and then draw my first spectrum. The numbering system is starting from 1. So the first one is H001. So this is my draw command for the H001. So here you see H001 got drawn. Now I want to draw the banana gate that is around this neutron region. So I select view and toolbar, and then I see the scissors tool. I click that and that gives me the graphical cut. So I draw it like this. At the last point, you know that you have to click twice at the same spot, not double click but two single clicks at the same spot. That closes the T-cut, and now I need to rename and then I need to save it. These are the two operations which I have to do. By default it is called cut G, so I am going to change it like this, and then I am going to write it like this way. So this is the command, and here it is, you see. So first I set the name and then I write it. So this completes the part for the first detector. Then I go to repeat it for the second detector. So when I want to repeat it for a second detector, all I have to do is to recall the command from here, but now I want H002, so I make this H002 and then I draw it, and so you will see the change in the canvas. It has changed from H001 to H002. Now again I select the scissors tool, and then I draw the cut around. I have very little statistics. In your case, when you have real files, you would be able to have more statistics. So this is drawn, and now I go to, again I recall this previous one, but now it is my cut N002, not 1. So I have to make two changes here. That's it. Now this will write the second one also. So that's how it got written. Now you just simply repeat this thing for all the detectors. This is, I have shown you up to 2 detectors. You got to just do this for all the 73 detectors or whatever number you have. And then when you finish doing that, then you must close the T file. So that command I have given for you in my PowerPoint. At the end, when you have finished repeating it for all the detectors, then you close it. I am closing it now, but then I won't have done for all the detectors, and you should do it for all the detectors, and you can also close and repeat and then do it anytime for the remaining ones, but you have to complete it for all of them. So you just close it like this, and then you quit root. So that's the process by which you would have done almost everything you need before the final round. So I'm going to close this video now, and we will start from the next one, where we go into the final round, where we will generate all the neutron spectra after applying all these cuts, and also we will take care of the slicing of the MWPC. So thanks for watching, and look forward to seeing you in the next video.